Section 6.7 is applications or models of exponential and logarithmic functions. So real life uses of exponents and logarithms. First question. So first 4 or 5 questions here are going to be about money. How does money interact exponentially and logarithmically? If $6,000 is invested in a bank account at 7% per year, find the amount in the bank after 12 years if the interest is compounded annually. Okay, so I'm going to go to a fresh screen where we have room to write here. And 6.7 here. Number 1, so it's $6,000 invested at 7%. And so the first part, we'll call it part A, even though they don't have letters there. If it's 12 years compounded annually. So here's the formula for the amount of money in compound interest. This is the compound interest formula. So for compound interest, we're going to use this formula again and again. A equals P1 plus R over N to the NT, where P is the principal invested at the start. The A is the amount later. The R is the rate of interest. The T is the number of years. And the N is the number of compoundings per year. So N equals 1 if it's compounded annually. N equals 12 for monthly. N equals 4 for quarterly, because that's 4 times a year. 3. If it was daily, that'd be 365 if they have daily compounding. So those are the variables. All right, so let's do this problem then. So this one we're working on is 12 years compounded annually. So annually means N equals 1. So we're going to use the formula A equals P 1 plus R over N to the NT. $6,000 is invested. That's the principal. So the amount will be 6,000. 1 plus R over N. The R is the interest rate. That's 7%. We've got to change that to a decimal, 0.07. Over N. N is just 1 in this problem because annually is only once a year. To the N. So N goes in 2 places. It goes here and here. Times T, how many years? 12 years. That's our T. So there's what we're going to put. So in the calculator, I can simplify this a little bit. 0.07 over 1 is just 0.07, and 1 times 12 is just 12. And then we can even clean it up again. This is just going to be 1.07 to the 12th. So hit the buttons on your calculator on that one. I'm doing it as well. And I'm getting $13,513.15. They want us to round to the nearest penny. So there we go. That's part A. Let's go on to part B. So part B, we're going to use the same formula. So we're still on number 1 here. Part B, we're doing $6,000 at 7%, 12 years, and then the part that's new on this one is the fact that they say compounded quarterly. Quarterly. So that means n is 4. N is, remember back here, n equals 4 is quarterly, because that's 4 times a year. If you compound your money quarterly, then you do it every quarter, you do it 4 times a year. 4 times a year. All right, so we'll use that same formula. A equals P, 1 plus R over N to the NT. P, the principal is the 6,000. The interest rate is 0.07. The N is 4. The N is 4 up there again. And the number of years, T is 12. 12 years for N. So let's clean that up a little bit. That'll be 6,000. The inside 1 plus 0.07 divided by 4 is 1.0175, and 4 times 12 is 48. Hit the buttons on your calculator. You will get 13,797.59. All right, part C. It's going to be very similar. This time it's compounded, same exact setup, but on this one it's compounded monthly. So now your money's compounded every month, and meaning interest is paid. Growth is given on the money every month. So this is going to be same formula. Just keep using the same formula for compound interest. P is the same. It's the same $6,000. The interest rate is even the same. It's still 7%, but this time N is 12. So I'll put a 12 here and a 12 there. The time is still the same. That's still 12 years. This is T. This is N. So simplifying that, we get 6,000. I'm just going to leave it 1 because I think it comes out some decimal that goes forever. So I'm just going to leave it 0.07 over 12. And that would be the 144 power. So just put it in like that on your calculator with parentheses. Type it in just like you see it with the parentheses. You'll get 13,864.32. So there's the answer for that one. So now for part D, the last one, things are going to be a little different. For part D here, they say we're still putting in, it's still $6,000 at 7%. That's our interest rate. For 12 years, that's still, but now it's compounded, not monthly or quarterly or annually, but it's compounded continuously. Now, what does that mean? Compounded continuously. Well, when they say for that word, that's a key word we're going to want to watch for in this section when it comes to money and when it comes to living things or substances growing or shrinking. Same thing. When you see the word continuous, that always means we're going to use a different formula. We're going to use this formula, what I call the PERT formula. A equals PE to the RT. So a little bit different formula instead of the one we've been using. This is only for continuous. So you see the difference. Let me look back here. So in part A here, it was compounded annually. So we use the big formula, N is 1. Part B, compounded quarterly. Big formula, N is 4. Part C, compounded monthly. Big formula, N is 12. But now when they say compounded continuously, we have a different formula we use. So A equals PE to the RT. You can learn in calculus where this formula comes from and why it's true. But for now, we don't have all those skills. We'll just use it. So A equals And let me go back over here. So what is the P? That's the 6,000. It's the same. P is still the principal. E, now E is the special constant. Yeah, I guess I don't need parentheses, do I? E is a special number. R, what's the interest rate? 0.07. T, what's that? That's 12 years, right? The interest rate is there. The time is there. So on your calculator, this is going to be 6,000 E. 0.07 times 12, that's 0.84. Like that. Now hit the button. So on your calculator, it's a little different. You might have to hit second and the natural log button, because right above the natural log button is the e to the x usually. So you got to get that thing that's above it. So usually that's how it works on most calculators. And then the 0.84 and then equals. So I'm doing it right now too. I'm getting 13,898.20. Like that. There we go. There's the answer to that one. So notice how these amounts get a little bit larger. Each one's a little bigger than the last one, right? The answer to A was 13,513, and then 13,797, then 13,864, and now 13,000, almost 900. Got a little bit bigger the more frequently we compound the money. Right? We started by compounding, paying interest on the money we have invested only once a year, annually. Then Part B went to quarterly, 4 times a year. Part C went to monthly, 12 times a year. And now Part D is continuously. That's the most frequent you can compound. That gives us the most money. There we go. Number 2. Here, let's go back to see number 2 back here. There it is. You deposit $2,000 in an account paying 2%. Compounded monthly, so that's N is 12. How much will you have in 10 years? So it's the same formula, A equals P. I'm going to use the big one now. We don't use the PERT formula. That's only when it's compounded continuously, which will be problem 3. See that word? To the NT. Okay, so this is going to be P. The principal is $2,000. The interest rate is 2%. The N is 12, because monthly is 12 times a year. 12 times T, how many years? 10 years. So, let's bring that down here and simplify a little bit. It's going to be 2,000. 1 plus 0.02 over 12. I'm going to figure that power out. I always like to figure out the power 120. All right, so hit the buttons on your calculator, and you will get this answer right there. Here we go. So our $2,000 becomes $2,442. There we go. Okay, so now number 3, we're going to, this one says continuously. So this means we're going to use the PERT formula when it's compounded continuously. So this is principal, $3,000 times E, that special number. To the R, that special number is 2 point something, like pi is 3.14, and it goes on and on. E is a special number, 2.718, and on it goes. R, the interest rate is 8% right there. And the time, 10 years. So there we go. Let's hit the buttons on the calculator. Well, actually, first I would simplify 3,000, and then multiply that up there, and you'll get 0.8, hit the buttons on your calculator, and you'll get this answer right there. All right, so let's try number 4. On number 4, they're changing things up. Find how much money needs to be deposited now into an account to obtain $1,600. So I might be repeating here, but I want to go back. I don't know where I cut out. So I'm going to do this problem. This one is continuous compounding, continuously. So that means we're going to use the PERT formula. Whenever it says continuous compounding, we use the PERT formula, which is a principal is 3,000. That's the amount put in the bank. E, the interest rate is 8%. The time The time is 10 years. So that'll be 3,000 e to the 0.8. Hit the buttons on your calculator, you'll get this answer. Okay, so now, number 4. Number 4 is find how much money needs to be deposited now into an account to obtain in the future 1,600 in 9 years at 3.5% compounded semi-annually, 2 times a year. That means n is 2. So on this one, we're using the big formula again, P1 plus R over N to the NT, because it's not continuous compounding, it's twice a year compounding. So this is going to be P. Now, do we know the principal? Do we know how much money was put in the bank? No, we don't. The 1,600 is the future value. That's what you want to get in the future. That's A. That's what A means, the amount later. The future value, they call it. It's the amount later. A means the amount later. P is the principal that you put in now. P is the principal you put in the bank now. A is the amount it grows to be later. Well, they're asking us, how much do we put in now? What is P? How much is P? In order to obtain 1,600 in the future. So the A is actually the 1,600, and we don't know the P. So 1 plus, and do we know the R? The R interest rate, I think we do, 3.5. Move that back 2 places, bonk, bonk. It would be 0.035 over N. N is 2 to the 0.03, oh no, N. N again is 2 times T. What's time? How many years? There it is, 9 years. 2 times 9. So, what does that give us? We're getting kind of cramped here. So, I probably should go to a fresh screen on that one where I have a little bit more room to work. Yeah, better do that. Okay, so number 4 here. So where are we at? So we're having A is P, 1 plus R over N to the NT. And, okay. And so we said the principal we don't know. The amount, the future amount, is the 1,600. The rate, the interest rate, is 0.035 over N, twice a year compounding. T time is 9 years. Okay, so let's clean this up a little bit. This is 1,600 P plus 1.035 over 2 to 2 times 9, 18. I basically just did the 2 times 9 is 18 thing. Now, trying to solve that equation for P. How do we do it? Divide both sides by that whole parenthesis thing. 1 plus 0.035 over 2 to the 18, right? We've got to divide by that whole thing. And then we got to do all of that on our calculator. How do you do all that on your calculator? Well, there's a lot of ways, but let me give you probably what I would do. I would probably start with the, would that be easiest? Well, no, I would just start with the top, 1,600 divided by, and then you're going to go parenthesis, 1 plus 0.035 divided by 2, forgot the 2 in there, divided by 2, parenthesis, to the power, 18 equals. And when you do so, you'll get the answer, $1,170.85, rounded to the nearest penny there. 85 cents. So that's the amount of money that should be put in the bank at the start. That's the principal that will grow to become $1,600 9 years later. So that's how we do that problem. Okay. Let's go back to number 5 now. Number 5, find how much money needs to be deposited now into an account to obtain $9,000, future value again, in 9 years. If the interest is 3% per year compounded, there's that big word, continuously. So whenever they say compounded continuously, we know we use the PERT formula, right? The littler one, PERT. And so the amount in the future is the 9,000. That's over here. The A is the 9,000. We don't know the P. The interest rate is 3%. Right there, 0.03. Make that a little better there. And the time? What's the time? 9 years. So this equation becomes 9,000 is P e to the 0.27, right? 3 times 9 is 27. It's 0.27. Now we got to solve for P. How do we solve for P? We've got to divide by that e to the 0.27. P's alone. Hit the buttons on your calculator, and you will get this answer right there. Maybe it would help if I wrote out some of the calculator steps. It's basically going to be $9,000 divided by e to the power 0.27 equals. They may or may not. You don't really have to have parentheses around that 0.27. Oh, and to get the e, I should show you. You have to. Yeah, I should show that. So 9,000 divided by. You have to hit second and the LN button, which has the e above it. And that'll make it e. And there we go. You get that 6,870.42 on your calculator. All right, so number 6, find the time it takes for $5,000 to double when it's invested at an annual interest rate of 8% compounded continuously. So there's continuous compounding again. And so we want to figure out the time for doubling for continuous compounding. So let's go back here where we have some room. So, part A, $5,000 to double at 8% compounded continuously. So how long? Question is how long for 5,000 to double? All right, so which form of compounded continuously? You know we're using the PERT formula, right? And the 5,000 is the amount of money we're putting in the bank at first. It's the principal investment. What amount do we want it to become later if we want it to double? We want the $5,000 to double. We want to invest $5,000 and have it double. So if it doubles, it'll become 10,000, won't it? And the interest rate is 0.08, and the t, the time, is what we're looking for. Okay, so we need to solve that equation for t. Solve for t, find the time. So how do we get t alone? T's right here. He's saying, I want to be alone. Get rid of this 5,000, this e, and this 0.08 so I can be alone. Okay, well, first we get rid of the 5,000. Divide both sides by 5,000. Boom, and 10,000 over 5,000, we don't need a calculator for that, that's 2. Now, what do? We're trying to solve for t. T is up there in the power zone. So when the letter is in power, remember we learned in the last section, when the letter's in power, what do? LN. So step 1, LN both sides. Step 2, power drops down to the front. Remember that? Logs and powers are the opposites of each other. So if you got a power, use a log. You got a log, use a power. That's what we do. So we're going to come in here, we're going to go LN on this side and LN on that side. LN on both sides. And then that power, the whole power, will drop down to the front of the log. So it'll be 0.08t ln and the other side is ln2. And remember what ln is? ln just equals 1. This just cancels, or it's just 1, and multiplying by 1 doesn't do anything, so we might as well ignore it. So now we just have to finish solving for t, right? That's been our goal from the beginning, solve for t. So now just divide by 0.08. And boom, t equals, hit the buttons on your calculator, that's what I'm doing right now too. ln of 2 divided by 0.08, I'm getting 8.66. I don't know. Oh, they want 4 decimal places, so I gotta do a little bit more. Or I don't know. Yeah, 4 decimal places. So 8.6643. That's how many years? About 8.5 years, a little more than 8.5 years. 8.6643 years is how long it'll take the $5,000 to double and become $10,000 if you invested at 8% compounded continuously. Now in part B, we're going to do kind of the same thing. So here's 6B, and they're saying how long for 500,000. So part A said how long for 5,000 to double. Part B said how long for 500,000 to double at same conditions, 8% compounded continuously. 8% compounded continuously. So you know the formula we're going to use. Whenever it's compounded continuously, you use the PERT. So what's the principal being put in? Well, $500,000. And what's the amount we wanted to remember? The A is the amount it becomes later. So if you want to double $500,000, it'll become $1 million, right? E to the R is 0.08, and there's T. We want to solve for T. Just like the last problem, we're trying to solve for T. Here we go. What's the first step to get T alone? Divide off the 500,000. Cancels out. E to the 0.08T. And so what is $1 million divided by 500,000? It's 2, right? 500,000 goes in there twice. Notice at this point we have the very same equation we had right there. You see it's going to be the same. The answer is going to be the same. I'll do it just to finish it up. We just do ln on both sides, right? That's what we do when t's in power. The whole power then drops down, right? We get 0.08t, ln e, ln2, ln e is 1. How do we finish getting t alone? Divide by 0.08. That's the same thing we did on our calculator last time. The time is going to be exactly the same. 8.6643 years. So you see, the point of this having a part A, part B is to help you to see that it doesn't matter the amount of money you put in. If the money is put in at 8%, right, 8% compounded continuously, it'll take 8.6643 years to double it. It doesn't matter what amount started out. That's the doubling time. That's how long it takes to double the money. That's the point of that example. Okay, we're going to change gears, going on to number 7 here. So those were all, 1 through 6 were the money problems. Those were all dealing with money. Now, starting at number 7 through 15, we're going to shift to like bacteria and populations, living things, more biological examples. So that 1 through 6 was economic, money examples, and then 7 through 15 are going to be from chemistry and biology examples. So let's say a bacteria culture initially contains 3,000 bacteria and doubles, that's a key word there, every half hour. Find the size of the bacteria population after 60 minutes. Find the size of the bacterial population after 7 hours. So basically, if your population is doubling every half an hour, that's exponential growth. Exponential growth. Exponential growth means it's multiplying by the same number every period of time. So if you're doubling, you're multiplying by 2 every 30 minutes, half an hour, right? Whereas linear growth, so the graph is going to blow up like that, exponential, like the graphs we did of exponential functions earlier in this chapter. So that's exponential growth. As opposed to that would be linear growth. Linear just adds the same number every time, whereas exponential multiplies the same number every time. Doubling is multiplying every half an hour. If we said the population goes up by 500 every 30 minutes, that would be linear. It would just go up by 500, then 500 again, then 500 again. Whereas doubling, that's going to be a lot more powerful growth. That's going to make it curve exponentially up, 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 and away. So doubling, anytime you multiply, that's exponential growth. Okay. And what formula do we use for exponential growth? A equals, well, you can use different versions. I'm going to use what we used in the last chapter, or in the beginning of this chapter. A times b to the t. Remember that formula? Y equals a times b to the t. Now the trick is, for doubling, it's going to be like this. It's always going to be a times b, and the b will be 2, automatically. The b will be 2, and the time will be t divided by the doubling time. So there's the setup. It's always going to be that way, which will be the same thing on the next problem, because they're going to talk about doubling in the next problem. So it's always, and A is always the starting amount. Starting amount. So the amount that it starts out to be times 2, that's for the doubling, that's multiplying by 2, to the time divided by the doubling time, whatever that is. So that's the setup when it's doubling. Let's get into the particulars now. Let me get this stuff out of the way, and we'll go for the particular information. So in particular, it's going to be, what's the starting amount? Initially contains 3,000. So our A is 3,000 times 2 to the t divided by, and what is the time? It doubles every half an hour. Now we want to go to minutes. Why? Because down here they're going to mention minutes. Really, you could do it all in hours, or you could do it all in minutes. It doesn't matter. I'm just going to go to minutes. So half an hour will be 30 minutes. I'm going to change that to 30 minutes. So do you see what I did there? I did the starting amount, which is 3,000, times 2 to the t divided by the doubling time, and the doubling time was 30 minutes. So I'm doing the problem in minutes now. So there's my formula. Now what do they want me to do with it? They want to find the size of the bacteria population after 60 minutes. So plug in 60 right there for t. And so we'll get 3,000 times 2 to the 60 divided by 30. And that's 3,000 times 2 to the 2, isn't it? 60 divided by 30 is just 2. So that's 3,000 times 4, right? 2 to the second power is 4, so that's 12,000. So the answer to this first part is 12,000, which is what they say right over there. 12,000. That's the size of the bacteria population after 60 minutes, of course, right? That's just half an hour twice. So it's 3,000, a half an hour later it becomes 6,000, a half an hour, right, because it doubles every half an hour. So half an hour later it becomes 12,000. That's 1 hour later. Of course, we could have done that one without using any fancy formulas. We'll need the formulas in a minute, though. Now let's do part B. Find the size of the population after 7 hours. Okay, so that'll be a little bit harder. Okay, so I just erased that answer there. Okay, so let's try this one. So it's going to be y equals a times 2 to the t divided by, 30, right? 2 to the t divided by 30, because 30 minutes for doubling. Oh, and the 3,000 goes in the front. Yeah, let me let me get it straight here. It's 3,000, the initial amount, times 2 to the t divided by, what's the time to double? 30 minutes. So there's our formula, and they're saying find it after 7 hours. Well, 7 hours, that's going to be 7 times 60 minutes in every hour. That's 420 minutes. So plug in 420 right there for t. And so what does that equal? 3,000 times 2. If you divide that on your calculator, I think you get 14. Yeah. And then hit the buttons on your calculator. 3,000 times 2 to the 14th power. And you will get this whopping number, which is 49,152,000 bacteria just 7 hours later. See the explosive exponential growth of the bacteria on that problem. Okay, let's go to number 8 now. So, coming over here. Problem number 8. Let me get this out of the way here. So, on question number 8, it's going to be the same kind of thing. The doubling period of a bacterial population is 20 minutes. So what does that mean? So we're going to use the same kind of formula. It's going to be y equals a times b to the t, but in specific, they're telling A is going to always be the starting amount. So what did it start out with? The bacterial population, they're not telling us the starting amount, so I'll just leave it as A, right? They're saying the doubling period, in other words, how long it takes to double. The doubling period is 20 minutes. So 2, the b becomes 2, to the t divided by 20. Remember, that's how we do this. That's the general game plan. You're going to multiply by 2, and then you divide t to the power, t divided by 20. That's doubling time. So that's the general setup. We always go y equals a times 2 to the t over doubling time. And the a is the starting amount. So that's how we do the doubling. Y equals a times 2 to the t divided by doubling time. So y equals a times 2 to the t over 20 power. And then they tell us also that at 100 minutes, let me come over here, at 100 minutes, the population was 60,000. So the population, 60,000 at time 100. See what I did there? I plugged in 100 for t and 60,000 for y. When the time went to 100, the population, the y, went to 60,000. All right, so let's take that formula over here, and we get 60,000 equals a. Actually, I'm out of room here. Let me take this to some fresh space here. So number 8. I should have done this from the beginning. Doubling time, 20 minutes at t equals 100. The population was 60,000. Okay, let's start again here. So in general, these formulas are always going to be a times 2 to the t over doubling time. So this is what you want to put on your note card for the next exam, is this doubling time formula. And a is always the starting amount. Okay, So here we go. Y, oh, and so they're telling me the Y, the amount Y, 60,000 is the population when T is 100. So 60,000 is the population. When T is 100. And the doubling time is 20. Right? The doubling time, 20 minutes, that goes right here. So how does this equation break down? We get 60,000 equals A times 2 to 100 divided by 20 is 5. So that's 60,000 equals A times 32. If you take your calculator, 2 to the 5th power is 32. Let's solve for A. Divide both sides by 32. I'm going to use my calculator, 60,000 divided by 32. And I'm getting 1875. So that's the A, and the A is the starting amount. So the starting amount, that's their first question, part A. What's the starting amount? It is 1875. Now, part B says find the size of the population, at T, let's say after 3 hours. So 3 hours. Now remember, we're using minutes, right? We've been using minutes so far. So we have to change that to minutes. 3 times 60 equals 180 minutes. So they want me to take the formula that we got right here. Y equals A times 2 to the T over doubling time. And now we know the A is 1875 right here. 1875, that's the starting amount, times 2 to the T over 20, because 20 is the doubling time. So there's the formula. Now they want me to plug into it 180 minutes for T. Times 2 to the 180 divided by 20. That's going to be 2 to the 9th. 180 divided by 20 is 9. So use your calculator. 1875 times 2 to the 9th. Y will equal 960,000. That's quite an explosion in the bacteria population. That's what we mean by exponential growth. It explodes. Okay, so to number 9 we go. Number 9, the half-life. So now we're changing gears from those last two problems were about doubling. Now we're talking about half-life. The half-life of radium-226 is 1590 years. So what does half-life mean? Half-life. Well, half-life is how long it takes for there to be half of it. It means after 1,590 years, this radium-226 stuff, half of it will go away. So, for example, if you start off, well, they're saying 500 milligrams. Sample contains 500 milligrams. It'll drop to be half that amount, so 250 milligrams after 1,590 years, a long time, 1,590 years. Half of it will just go into the atmosphere. It'll dissipate into the atmosphere. So if you have a lump of this radium-226 sitting around in a chemistry lab or out in the world somewhere, you have 500 milligrams of it. It'll break down over 1,590 years to be half that, and then half of 250, half of $2.50 is $1.25. It'll break down to After 1,590 more years, it'll break in half again. Half of it just keeps going away every 1,590 years. And then again, half of $1.25, I don't know what that'd be, 62.5, I think. It'll break down after another 1,590 years, etc. So every 1,590 years, half of it goes away into the atmosphere. That's what it means that the half-life of radium-226 is 1590 years. That's how they measure chemicals. We can see it down here. Half-life of palladium-100 is 4 days. Every 4 days, half of it goes away and half is left. And down here, number 11, carbon-14, half-life is 5,730 years. So this is how they deal with chemicals a lot. We're doing chemistry now, is the half-life of a substance. Well, let's go solve that problem. Let me get some fresh space here. So for number 9, so the half-life of the radium stuff is 1,590 years. And a sample contains 500 milligrams. How much? How much after 1,000 years? So after 1,000 years, how much will be left? Well, so remember the equation we've been using, A times B to the T for exponential. So this is also exponential. So remember what exponential is? It's when it's multiplying by the same number every time. So this is multiplying by a half every time. The last two problems, number 7 and number 8, were doubling, right? They were about number of bacteria doubling every however many minutes, 100 minutes or 20 minutes or whatever. So now we're talking about halving. So this is decaying. It's going down. This is exponential decay. These other two, 7 and 8, were exponential growth. And all the money problems were growth as well. So now we're going down. We're going half as much every 1,590 years. It's still multiplying, so it's still exponential. We're still going to use, the t is up there in the exponent zone. It's an exponential equation. Now you can probably guess what the A is. Let me rewrite it here. The A is the starting amount, like usual. Starting amount. The B, now in the last problem for doubling, the B was 2. So what do you think the B is going to be for halving? What's a half? You could write the fraction a half, but it'd be easier to use a decimal. What's the decimal for a half? 0.5, right. Now what's it going to be? T divided by the half-life time. So see how it's the exact same formula as the doubling formula? Let's look back over here. It was the starting amount A times 2, because that was doubling, to the power T over the doubling time. Well, now for halving, it's times a half to the power T over the half-life time. It's the same exact formula, just for halving instead of doubling. So that's no surprise. So there's the formula we're going to use for all the half-life problems, just like the one we used for the doubling problems. So let's go to it. We're going to have y equals the starting amount, 500 milligrams, times 0.5 to the t, divided by what's the half-life? 1590 years. So there's our formula, and they're saying how much after 1,000 years. So take that 1,000 and plug it in for t there. So we get y equals 500 times 0.5 to the t, which is 1,000, over 1590. So type that into your calculator. It's going to be 500 times 0.5 to the power 1,000 divided by 1590 equals, I'll do it right now as well, and I'm getting 3 323.3277 to 4 places milligrams. That answer makes sense, doesn't it? Because remember, originally there were 500 milligrams, and after 1,590 years, it would go down to half that amount. It would go down to 250. So after 1,000 years, it won't go all the way down to 250, right? That's less than the 1590 years. So it won't go all the way down to 250. See how the answer's above 250? It's gone down. It's gone down from 500, but not all the way down to half. It's only at 323 milligrams left after 1,000 years. That answer seems reasonable. Okay, let's go to number 10. So the half-life of the palladium is 4 days. After 12 days, a sample has been reduced to a mass of 2 milligrams. What was the initial? What is the mass 4 weeks after the start? And how? Oh yeah, it just wants those two things. All right, let's get some fresh space and work on that. So number 10. So half-life of the palladium stuff. The half-life is 4 days. After 12 days, after 12 days, the sample is reduced to 2 milligrams. Okay, so here's the first question. Question A. What was the initial mass? What was the initial mass? Like, how much was at the start? That's what initial means, right? At the start. How much was at the start? Well, we're going to use the equation y equals a times b to the t. The starting amount we don't know. The b is the half, right? So 0.5. To the t over the half-life. And so what is the half-life? 4 days. So there's our formula. Now they're telling us that after 12 days, so when t is 12, the amount was 2 milligrams. So 2 equals whatever the starting amount is times 0.5 to the t, 12 over 4. So that means 2 equals a times 0.5 to the 3. 12 divided by 4 is 3. Now use your calculator. I'll bring it up here. 0.5 to the third is 0.125 on your calculator. Then finish solving for A. Divided by 0.125. And actually, you know what? Maybe I should have just brought this down here. I'll just bring it right here. Like that. Get rid of it from here. And let's finish. We now divide by the 0.125. And we get A is 16. A is 16. So that's the starting amount. Now part B asks the question, the second part, what is the mass 4 weeks after the start? Weeks after the start. So using the equation, y equals a times 0.5 t over 4. But now we know what a is. A is over here, 16. So now we can plug in the a. So there's our equation, and they're asking us 4 weeks. 4 weeks, 4 times 7, right? There's 7 days in every week is 28 days. You got to watch the time units. Remember, you can't change time. So we started the problem in days right here, 4 days. So that means everything else has got to be days. We could have done the problem in weeks. It doesn't matter. You can do whatever time unit you want. You just have to be consistent. So it's got to be days everywhere or weeks everywhere. We already started with days, so we got to keep going with days. So I got to take their 4 weeks, change that into 28 days, plug that in right there for t. So we get y equals 16 times 0.5 to the t, and what's t? 28 divided by 4. 28 days. So y equals 16.5 to the 7th. Hit the buttons on your calculator, and it'll come out 0.125. 0.125 is the answer on that one. So there we go. We found the amount after 4 weeks. Okay, back to number 11 now. Onward we go. Number 11, a wooden artifact from an ancient tomb contains 55% of the carbon-14 that is present in living trees. How long ago to the nearest year was the artifact made? The half-life of carbon-14 is 5,730 years. So this is carbon dating. So we're going to see mathematically how they do carbon dating, how they try to figure out how old something is. So basically, here's the deal. When they find something living, basically the minute a living thing dies, scientists have discovered that the amount of carbon-14 in the blood or inside the living object begins to decay, begins to go away into the atmosphere right then. And they know that the half-life of carbon-14 is very long, 5,730 years. It's a long half-life. It takes 5,730 years for carbon-14 to half of it go away. So however much you have, half of it goes away every 5,730 years. So it's like a time clock. They can find something that's died, like a tree, a dead tree, and they can find when it died, because the minute it died, at that moment, its carbon-14 began to break down, began to dissipate into the atmosphere, but not very quickly. It only loses half of it every 5,730 years. So if they can find out what percentage of its carbon-14 it has left, then they can figure out how old the thing is. That's what we're going to do here. This is carbon dating. So let's go do that one. So number 11. Carbon-14, half-life, 5,730 years. Okay, and the wooden artifact has 55%. The wooden artifact from an ancient tomb contains 55% of the carbon that is present in literature. Yeah, it has 55% of its living carbon-14. Right? Well, it's not a very clear sentence. It has 55% of the carbon-14 in living trees. So we know it's only got 55% of its carbon-14 left, comparing it to trees that are currently alive. It has 55% of its carbon-14 left that it originally had when it was living. So how old is the tree? How old is the tree? or we should say, how long ago did the tree die? How about that? Because that's what we're really getting a clock on. How long ago did the tree die? That's what we're really going to be able to answer. Okay, so we know the formula y equals a times b to the t, right? Anytime you're multiplying by the same number every time, that's exponential. We're multiplying by a half every 5,730 years. So we take a, the starting amount, times 0.5, because that's the half, to the t over, remember it's t over the half-life, and so in this case, 5,730 years. So there's our formula. Now, we don't know the starting amount. We don't know A. But here's what we know. It has 55% of its carbon-14 left, so we're going to take that and plug that in here. Now, here's the mistake a lot of people make. They go 0.55. They change to a decimal, and that part's correct, 0.55. Just like that. Now that's mistaken. Why? What's wrong with that? Well, you have to put an A here. Why? Why is it point? How do you know there's supposed to be an A there? Well, because think about this. What if I said to you all of a sudden, 55%, 55%, just like that, and I stop, 55%. You would think, well, 55% of what? Exactly. Of what? Percentage, is a part of something, right? And so you have to have something with it. You can't just have 55% or the decimal, 0.55. You can't just have that alone. That'd be crazy. 55% of what? Of the original, right? It's 55. It has 55% of the carbon-14 in living trees, the original, or starting amount. It's got 55% of, and of means times in math. It's got 0.55 times the original. What's the original A? Remember, A is always the starting amount in all these exponential formulas. So it's 0.55A that goes there. The amount is 0.55A. It has 55% of its original times A. Okay, now why does that matter so much? Well, that way, right away, we can just divide off the A. You see, you have to have the A on both sides so you can get rid of the A. So now we've got 0.55 is 0.5 to the T over 5730. All right, what in the world, how are we going to solve? So let me get rid of this here. We now need to solve for T. How do we solve that equation for T? We're trying to solve for the time, right? How long ago the tree died. How do we find the time there? Solve for T. T's up here in the power zone. Right. So what do we do when our letter's in power? When T is in power or X is in power, remember the last section? We solved exponential equations. When T is in power, step 1, ln both sides. Remember, logs are the opposites of powers. So if you got a letter in power, you got a natural log both sides. And then step 2, the power drops down to the front. So I'm going to go ln on both sides, and then this entire power, the fraction, the T over 5730, will drop down. Let me, I have room there. So I have ln of 0.55 equals T over 5730 times ln of 0.5. So we got the T out of power. Now it's just multiplying the front of the natural log. So let's bring it up here. Got a little bit more work to do, not a lot. ln 0.55 is T over 5730 times ln of 0.5. All right, first step, we're trying to solve for T, right? Let's divide both sides by the ln of 0.5. And that cancels. So we get T over 5730 equals ln 0.55 over ln 0.5. Okay, and now last step in order to finish solving for t is multiply both sides by 5730 over 1. Here, let me separate these here. And same thing on this side. I'm kind of running out of room. Put the equals over here. 5730 over 1 on both sides. And so t equals 5730 times ln of 0.55 over ln of 0.5. Hit the buttons on your calculator. I'm going to do it now too. 5730 times ln 0.55 divided by ln 0.5. I'm getting 4942. They want me to round to the nearest year, so 4942. That's how many years ago that tree died. 4,942 years ago. Almost 5,000 years. It makes sense it's under 5,000 because it's still got more than half left, just barely, but more than half. It hasn't gone all the way down to half. That would take 5,730 years. So it must be a little bit less than that. Makes sense. 42 years. And it happened. So we canceled these out here. We got t alone here. And then hit the buttons on your calculator. So there we go. Let's go to number 12. So number 12, the fox population. The fox population in a certain region has a continuous growth rate of 8% per year. It is estimated that the population in the year 2000 was 24,100. Find a function that models the population t years after 2000. Hint, use an exponential function with base e. Yeah, that's a really important hint. Basically, so this is something new. I want to make sure you catch this. This is important on this problem and the next one. We're going to have kind of a special deal, and that is they're using a special phrase here. It's this word right here. We've seen it earlier in this section, right? In the beginning of this section, continuous. Whenever they say continuous growth rate, remember that meant we used the PERT formula. Remember that earlier? We used the PERT formula when in the money ones. Back when they said continuous compounding, we used the PERT formula instead of the other formula, instead of the one that was P, 1 plus R over N to the NT. So we don't use that one. We use the PERT formula when they say continuous. Well, likewise, when they say continuous for populations growing, biology or chemistry, same thing as economics, money, same thing. You got to use this PERT formula, not the other one, not the one that is y equals a times b to the t, not that one, and not this one. You're going to use the PERT formula. So that's what you have to be really clear on this material. If they ever say that something is continuous growth or continuous compounding, we've got to use the PERT formula. You've got to have the E. That's what they're giving you the hint. The function with base E. You've got to use that, not any other formulas. Okay, so how do we use the PERT formula? We'll just pretend it's money, basically. It's the same thing. It's just biological objects instead of dollars, but it's the same thing. You know how it works, right? A is the amount later. P is the principal invested at the start. Okay, so the formula then, it started off, it says, the rate is 8%, so that's going to be the R. And it's saying that in the year 2000, it started off at 24,100. It wants me to use times 0 for the year 2000. So the formula is going to be principal, the starting amount, which was 24,100, Here, let me change colors, be a little more clear. 24,100 e to the 0.08, that's because of the 8% for r, t. That's a t up there in the power zone. 0.08 t. So there's the formula that we're going to use, the PERT formula. Now, on part B, they want me to actually use it. So I'm actually going to use it now. Part B, they say, okay, the year 2008. So they want me to, you can see this right here, time is 0 in the year 2000. So in 2008, that's 8 years after 2000. Remember, on these kind of science problems, they always have a starting time. They're starting in the year 2000, and so that's the starting point. So 2008 is 8 years later, so plug in an 8. So take the formula, y equals, or amount equals, or population equals, whatever you want to call it, 24,100 e to the 0.08 t. So grab that 8 and plug it in right there for t. So we're going to get 24,100 e to the 0.08 times 8. So bring it up here. That's 24,100 e to the 0.64. Hit the buttons on your calculator. That's what I'm doing now too. And I'm getting 45,705. Yeah, exactly what they got here. They want me to leave it just like that, rounded to the nearest integer. The whole number of foxes. There we go. So the key difference on this question, it's like the other financial ones, when they say continuous growth, like continuously compounded interest, you got to use the PERT formula in that situation, not any of the other formulas. Let's try number 13. It's going to be similar. Population of a country was 260 million in 1991, and the continuous, there it is, that means we're going to use A equals P e to the RT, the PERT formula, continuously compounded interest, or continuous growth. Exponential growth rate was estimated at 3.1% per year. Assuming that the population of the country continues to follow exponential growth model, find the projected population in 1999. Round your answer to one decimal place. So here we go again. So we're gonna use P, the starting amount, 260 million. E, what's the rate? That's what, move the decimal back 2 places, 0.031. Whoop. 0.031. Oops, I'm getting scribbly there. T. 0.031 T. And now, remember, there's in these science problems, there's always a starting time. They started in 1991. So they're asking about 1999. 1999 is T equals 8 years later. Right? So you always have to know there's always a starting time. That's 1991. So then they're asking about 1999. That's 8 years later. Grab that 8, plug it in right there for T. So you're going to get 260 e to the 0.031 times 8. So that's 260 e. What's 0.031 times 8? I'm getting 0.248. Hit the buttons on your calculator. So it's 260 times e to the power 0.248. So on this one, I'm getting 333.2. Yeah, they want us to round. Here's the answer right there. Rounded to one decimal place. I guess they didn't really say. Oh, yeah, they did right there. One decimal. So 333.2. So that's how many million people will be in the population. So they're saying this population is growing at 3.1% continuous. That's continuous. That's why I use the PERT formula. Continuous compounding interest or continuous growth, we use the PERT formula. So that, if that's the case, then 260 million people in 1991, 8 years later, 1999, will be 333.2 million people. That'll grow quite a bit. Okay, 2 more questions left. So those 2 questions we learned about continuous growth. Now, number 14, a radioactive substance decays exponentially. So it's going down. A scientist begins with 200 milligrams after, and then it says after 21 hours, 100 milligrams remains. How many milligrams after 34 hours? Okay, let me get some fresh space and we'll give this one a go. So, number 14. So, it begins with 200 milligrams, and then after 21 hours, it's down to 100 milligrams. Whoops. It's down to 100 milligrams. How many? How much after? How much after 34 hours? Okay, it's a pretty straight ahead question. Now, which formula are we going to use? Did they say continuous anywhere on this one? No, they never. If you go back to the words, they never said continuous growth rate. They never said that. So, do not need to use the PERT formula. Do not need to use the PERT formula, right? That's only for continuous growth. So instead, I'll just use the A equals, or Y, whatever you want to call it. Doesn't really matter what that letter is in the front. I'm going to use just the normal one, A, B to the T. All right? Use that one. Don't need to use the PERT one because they never said continuous growth rate percentage. So I'm going to use this one. Now, did they say doubling on this one or halving? They did not. So this problem's a little more tricky than the other ones we did because they never said, here's the half-life, here's how long till it's half, or here's the doubling time. So we're not going to do that. It's not a doubling time or a halving time. So first, this is going to be a harder one. First, we must find B because it's not 2 and it's not 0.5. So it's not like the other ones. So far we've always had a doubling time or a halving time, or we did the PERT for the last 2 problems because it was continuous growth rate that was given to us. But on this one, there's not a continuous growth rate. It's also not doubling. It's not halving. It's just special. So we have to do some extra work on this one. First, we have to find B. So let's use this formula. How are we going to do it? Well, it begins with 200. So the A is 200. That's where it begins. So the A is 200. That's the starting amount is the A. And then they tell us that after 21 hours, it's at 100 milligrams. So 100 milligrams at 21 hours. So 100 milligrams at time 21 hours. So plug in 21 for T and Y is 100 milligrams. Now what we're trying to do here, we're trying to find B first. So we're going to try to find B. So how can you solve for B? So first thing is divide by the 200, right? So that's going to be, if you divide that by the 200, that's going to be 0.5 is B to the 21. And now, what are we going to do to finish that? Well, how do we get that 21 off of the b? What's going to get rid of that? Because I want to get b alone, right? I'm trying to solve for b, get that 21 off of the b. How do I get that 21 off of the b? You can raise it to the 1 over 21 power. 1 over 21. And it'll cancel out right there. And so this is gone. And b is 0.5 to the 1 over 21. So now, let's bring that up here. Now, so this is the first phase. So I just did the first phase. First, I had to find b. Got it. I got b. There's b. It's 0.5 to the 1 over 21. Now, second, rewrite the formula, plug in b equals 0.5 to the 1 over 21. So let's write out the formula. What do we got now? It's y equals, this is part 2 here, y equals, remember it's right here, a times b to the t, but we've known the a is 200, and the b now is 0.5 to the 1 over 21, and then there's also a t out there, right? This t is also there. Now, what's going to happen with that t? Well, the t is over 1, we don't need to mess with it. We can just leave it like that. So now, let's finish up the problem from here. What's left to do on this problem? Well, they want us to figure out, if you go back to the question, how many milligrams, or it's right up here, how much after 34 hours? So grab that 34, plug it in for t. 200, 0.5 to the 1 over 21 times 34. So really, you can just put that 34 over 21, can't you? Because it's a whole number. Anything over 1 goes to the top. Anything alone is over 1 and goes to the top. So then on your calculator, you'll need to type in 200 raised to the power of... Well, wait, no, that's getting wrong. Let me try again. 200 times 0.5 raised to the power 34 divided by 21 equals. So there we go. 200 times 0.5 to the power 34 divided by 21. I'm getting 65 .11006035. That's more accuracy than we need. There we go. So that one was more tricky. It was in 2 parts, much harder problem. We had to do it in 2 phases. So why was this one harder? Because they didn't give us a half-life, right? It wasn't a 2, it wasn't a 0.5, it wasn't a half-life, it wasn't a doubling, it wasn't a PERT. Why not? Because it wasn't continuous growth. So it was just the normal a times b to the t, but we couldn't put in a 2 for b, and we could not put in a 0.5 because they never told us the doubling time or the half-life. So first phase is we had to do the work, which is normally just handed to us. We had to find the b ourselves by plugging in the initial information. That is 200 milligrams at the start, and then after 21 hours, 100 milligrams. Plugged all that in, found b is 0.5 to the 1 over 21. Put it back in over here. Then part 2, you rewrite the formula, plug in the b, plugged in the b with the t out there, b to the t, and then I finally plugged in the time to finish up the problem, the 34 hours, hit the buttons on the calculator. There we go, that's a hard one. Well, last one, number 15. A population of bacteria is growing according to the equation. Well, they just gave us the equation. Estimate when the population will exceed 2544. So they're saying, okay, here's your population at any time t. It is 1950 e to the 0.07 t. And they want me to, they're saying, when will the population be 2544? So plug in over here. 2544. And solve for t, right? They want to know when. That's t. It says it right here. Solve for t. All right, so how are we going to solve this little equation for t? We first off divide by the 1950. I don't know if that's clean or not. Let me see if I can divide those on the left. Oh, no, it goes on and on. I divided this on my calculator, and I got some decimal. Well, I guess I better write it. It's pretty long, so we want to use a lot of decimal places because we're not done with the problem yet. So when you have a decimal number in the middle of a calculation, when you got more steps to do, you better write down a lot. So we got that. Now, what are we going to do? What do you do when t is in power? How do you see how t's up here in the power zone? How do you solve for t in power? You ln both sides, remember, and then step 2, power drops down to the front. So you ln this side, ln that side. This whole power drops down to the front. So then we get ln of 1.30461538 equals 0.07 t ln e. That whole power drops down to the front. Ln e, remember, ln e is just 1 because they're opposites of each other. Natural log and the base e. So that's just 1. That's just gone. So last step to finish solving for t, just divide by the 0.07. Hit the buttons on your calculator, and you will get t equals 3.7986896, and that's plenty of digits there. And there we go. That's how we solve that one. And so we finish the last one.